Okay, here is the last topic of DNS is that getting your info into the DNS. So if you want to have your own domain name, for example, abc.nccu.edu.tw, and you have to register your name, for example, abc.nccu.edu.tw, to the authoritative name server, which is the name server responsible for wildcard.nccu.edu.tw, and you have to do DNS registration. But unless you are a very big organization or company that you are capable of setting up DNS server, authoritative name server. Otherwise, most of the people like us, we simply just buy a domain name from certain commercial company. So here is an example. Let's take a look at this one. In the internet, okay, there's a website called GoDaddy, and it sells a lot of domain name, and of course it is also set up several authoritative name server that is responsible for the domain names that sold by GoDaddy. And of course you can simply just type any names and see if GoDaddy has, for example, attack.com can be purchased on the GoDaddy website, and you can see that the money you need to spend is quite a lot, right? Set as 6 million New Taiwan dollar. But however, if you we know there are several different top level domain, right? For example, .tw, .com, .cool.city. There are some seldom seen domain top level domain names. So of course it is much cheaper. For example, attack.city, it only costs you 273 New Taiwan dollar per year. Okay, so if you buy those domain names from the GoDaddy.com, and of course it will help you to set up some A records and NS records on the authoritative name servers owned by GoDaddy.com. Okay, so that you can so that your domain name can be resolved by the authoritative name servers. Okay, so that is the last topic we'd like to talk about in DNS. Okay, so you can see that in chapter 2 we discussed several different application layer protocols. For example, we have HTTP, which is on the top of TCP, and basically it has two different messages. One is for request resources, the other is for response, and that's all, right? And the object, or we say the resources, will be included, will be encapsulated in the HTTP messages. Okay, that is one of the way that you can design your own protocol. Okay, the other way is something like SMTP. Okay, it is also a text-based. There's same protocol, but the communication pattern is a little different from HTTP, because HTTP has only one request and one response, but SMTP it's more like a conversation, right? A server and client need to communicate, need to exchange a lot of different messages through several different messages, right? And the actual email, the actual mail content will be embedded in the SMTP protocol. As we know, it is another RFC, another protocol, right? And of course, although there are several object will be included in one single email, but it uses a very special mechanism called multi-part, right? As we showed you before. So multiple objects can be embedded in one single messages, then that sent to push to the SMTP server and received by the UA. And we talked about that it is not necessary that the entire communication only use one single protocol. For example, you can send the email by using SMTP. You can receive the email by HTTP, by POP3, by MAP. It is very commonly seen ways for people who designed communication protocols. And of course, we have we introduced DNS, right? So this is built on the top of UDP, and only one request and only one one query and one response, right? Very short, very small packet. And we'll skip all of the security related topic in the first few weeks, because all those material will be covered later. Okay, will be covered later. The next topic is P2P applications, but in this section we will not go over any P2P protocol. We simply just discuss how good the performance, how good the P2P perform, and what is the concept of P2P when you want to send files, share files with another peers. Okay, so right here, P2P architecture, we mentioned a lot of different concepts last week, right? And here the first one is P2P has no OSON server, but for the current server architecture, the server should be an OSON server so that the client can find the server anytime, anywhere, right? So P2P has the arbitrary end systems can directly communicate with each other. For example, on the right hand side, we have 5 different P2P peers, and they can communicate with each other. But in the client and server architecture, server never talks to server, and client never talks to client, right? So peers request a service from other peers, and again, exactly the same peer can provide service in return to other peers. So we mentioned it before. If you have more and more peers, new peers brings new service capacity, and the new service demands, of course, because more peers need more service demand. And peers are intermittently connected and can change IP address, but in client server model, server should not change its IP address, and at least it should not change its domain name. Okay, so it's more complex to manage such kind of architecture, right? And as we mentioned before, P2P is very popular in the early 2000s, and at that time, VP file sharing and voice over IP is very popular. And I draw a figure right here is that, as I mentioned before, for communication, it is not necessary to use one single protocol. You can use multiple protocols, and again, it is not necessary to use one single architecture. For example, P2P or client server in the communication. So right here, the example is like that. Okay. Okay. Let's take a look at this one. Okay. So here we have A and B. There are 2 different hosts. Okay, and they would like to make for example a Skype call with each other. But if we mix up the P2P architecture and the client server architecture in this phone call, internet phone call, or we say VoIP, voice over IP application. Okay, for example, A can first communicate with the, for example, the Skype server right here by using client server architecture. Okay, by using the client server architecture. Right here, it should be the, it should be the blue lines, okay, which I draw here. Okay, so the Skype server may have a database, and they records the A is online, and what is the account name of the host A, and what is the current IP of A. So in the blue database, the A will try to register to the Skype server, say, okay, I'm online. And for B can use the green communication. Okay, use the green communication and talks to Skype server, say, okay, I'm online and I'm B, and what is my account and what is my current IP address. Okay, so after that, if A want to talk to B, okay, so right here the the green one is client server architecture, okay, and the blue one is also client and server architecture, right? But after A and B finish the registration process, so the Skype server both knows they both online, but when they want to communicate with each other, okay, if the voice packet, okay, transfer, or we say relay by the Skype server, as you can see, that is very inefficient, right? Because all the packet will be transmitted to the Skype server and then forward to the other peer, for example, B, right? But this application, for example, the VoIP application, the time delay is quite critical, so it spends more time to do such kind of relay, or say forwarding. So the performance, or say the satisfaction of such kind of application might be worse. Okay, so the other way is that A and B, after they do such kind of registration, they can obtain the information, right? They can obtain the information of the corresponding peers, which is A and B, and they can further communicate with each other directly using P2P architecture, because they can get the A or B's information from the Skype server, from the database, from the registration information, and then they can communicate with each other. So the red line right here is more like P2P architecture, and it is more efficient to do such kind of voice over IP application. Okay, I believe it's very easy to understand, right? So it is not necessary to use only one single architecture in your application. You can use both of them, P2P and client server. Okay, so here we have two pages that would like to show you the performance, the difference of the client server performance and the P2P performance when we transfer file. Okay, right here we can see that, okay, here we have a server S, right? We have a server S, and there is a very popular file, which is big F, capital F. Okay, this F bit file will be downloaded by all the other users, which I mean clients. Okay, this is the first one, second client, the ith client, and end client. we assume that there are n clients that would like to download the popular file f bits from the server. Okay, so that is, and the upload capacity of the server is US, and the upload capacity of each user is U1, U2, UI, and to UN, and the download capacity for each user is D1, D2, DI to DN. Okay, that is the setting. Okay. So the first one is we'd like to discuss the capability, the performance of client-server architecture. Okay, so we'd like to calculate what is the minimum time, or we say minimum delay, that in this such kind of file distribution. Okay, so here we have to calculate two values. Okay, the first one right here. Okay, you can see that this part is for the server. Okay, we analyze the server. Okay, as you can see that in total we have n files that will be downloaded from the server, right? So each file has f bits, so the total number of bits will be downloaded from the server is n times f, right? And what is the transmission rate of this server? That is the US, right? The upload capacity, okay, of this server. So for this server, it needs to upload in total n times f bit, and the capacity is the the upload capacity is US. So it takes nf over US second to upload all these files, right? Okay, that is the first part. And the second part is that is for the slowest client. Okay, we have n client, right? We have a lot of client right here. We have a lot of client right here, but there's always one client who has the slowest download capacity, download rate. Okay, so let's say the slowest download rate is D minimum. So for this specific client, if it should be the last client who get the entire file, right? So the time that the slowest client get a file is f over the minimum. So that is look like, and of course, in the system, it depends on the size of f, depend on the n, depend on the US and the D minimum. Okay, so maybe one maybe the first value is bigger, maybe the second one. So no matter what, we select the larger one. So this value should be the time to distribute f to n client using the client server approach. So it's right here. Okay, I think that's very clear. Okay, so but usually the size of the n should be a little bit larger, right? So if it is large, if it is a large number, so usually the bottleneck is the first value, not the second one, right? And it increases linearly in n, right? Right. Okay. So the next part is we would like to know what is the efficiency of P2P architecture. So right here again, we have a lot of different clients in this big P2P system, right? So that is the server, okay? And now we have three different values we need to know, okay? So the first, the second one, okay? The second one is still the same, okay? They're always a slowest client, okay? Maybe we should use the word peer, right? There's always a slowest peer who has the smallest download capacity. So for this client, okay, for all the other client, so all the other client has to wait this client to finish its downloading. Okay, so that is the second value right here. And again, it's a little bit different right here. The first value is to evaluate that this specific server, okay, this specific server, that is for the server. This specific server, okay, it needs to upload the entire F bit to the entire PUP system. So it takes F over US second, right, to upload one single copy of this file F to the PUP network. But right here, as we mentioned before, in PUP distribution system, okay, a file will be divided into several chunks, small chunks, and those small chunks can be downloaded or uploaded among all these peers. So, for example, for the for the very first few seconds, when the server upload the first chunk, maybe the first peer right here received this small chunk, the first small chunk, and after that, the server can upload the second small chunk to the second peer, and so on and so forth, so on and so forth. So server does not need to upload the entire F and all its chunks to one single peer. It's not necessary to do so. Okay, so those small pieces of chunk will be delivered to the entire N peers, and after the peer get the small chunk, they can share those chunks among each other, so they don't have to download the file F from the single server. They can download the file among all those N+1 source, right, including the original server and all the other N peers, right? So here we have the third value right here. For this system, for this P2P system, okay, all of those N+1 peers, they share N times F bits. So in this entire system, there will be N times F bits will be shared among this PUP network, right? So that's it, okay? But under what speed? As we mentioned before, now we have N+1 peers, okay? So US is the upload capability of the server, right? So sigma UI is all the upload capacity. We sum up all the upload capacity among all these N+1 peers. So at least, okay, for this system, N times F bits will be propagate, will be shared by using US plus sigma UI rate. So that is NF over US plus sigma UI. So that is for the system. As you mentioned right here, as aggregate, right? They download all the N times F bits. So that is, we have three values. So it depends on how many, depends on the different rate, USD minima and N, big N, capital N. So it depends on different values. So one of the three values will be the largest one. So that value will be the time to distribute F bit file to those N peers using PUP approach. Okay, so we simply just write down this value. We don't actually calculate it. But the textbook gives us one of the example that if you use client server approach, okay, every time you increase the one single client, okay, the minimum distribution time will linearly increase because you have one more client, right? But when you use POP architecture, okay, when you increase one more peers, okay, this peers, of course, this peers needs time to download the entire entire F bit. But while download the F bit, it will get the small chunks, right, in advance before it finish all the entire F bit, the entire F bit, right? After this additional peer get the more small chunk, it can then immediately share those small chunk to the other peers. So the demand is +1, for example, is +1, but it can also serve all the other peers in the POP network. So the entire capability of transmitting files, sharing files, increase as well. So the minimum distribution time is not linear as the client server architecture. Okay, this is just one of the example. So textbook or the slide, they have some concept of the POP file distribution, but we will not go over. But actually, the textbook does not contain any POP protocol introduction. They simply just they discuss how good POP file distribution is. Okay, for example, for BitTorrent, the file will be divided into 256K bits chunks, and the peers in torrent can receive and send file chunks among each other. And there will be a special peers called track peers. Okay, these peers will record how many users has been registered, what file has been downloaded from, will be provided by which peers, some information like that. Okay. So peers join torrent. Okay, it may have no chunks, but will try to download chunks from the other peers. Okay, register with the tracker and get a list of peers, and the new peers will try to connect to some its neighbor peers. Not all the peers, it's neighbor peers. So we say it is a subset of peers. Okay, while downloading, peers upload chunks to other peers. Peers may change peers with whom it exchanges chunks. Okay, so peers may come and go. Once peer has entire file, it may leave or may remain in the torrent to serve the other peers. So that is BitTorrent. Okay. So we will stop right here because there's some simple introduction. So take some time to take a look at the textbook or the slide right here. Right here we finish our second chapter, which is application layer protocol. But as I mentioned before, there are several different approaches to design a communication protocol. You can design a text-based protocol, you can design a binary-based protocol, you can design a request and a response messages, you can design a communication, we say interactive, like SMTP protocols. There are several different ways. So make sure you understand we have several different choices to implement communication protocol. So next time when you design your own protocol, for example, if you join a gaming company, you join a VoIP company, you join app okay, company, and maybe you have chance to design your own protocol. But remember, we have several different choices. So think about what is the most maybe convenient way, or maybe what is the most good design for your application. So we stop right here. We'll go to chapter number 3 next hour.